Good morning, good afternoon, or good evening, ladies and gentlemen. I hope you're doing very well today, and welcome to Unit 8A, which is called Electric Charges. And this is Unit 8A because the next Unit, 8B, goes hand in hand with this one. In Unit 8A, we will be talking about what electric charges are, how they work, and in Unit 8B, we will start talking about electric current and circuits. So without any further ado, let's jump right into Lesson 8.1, which is also titled Electric Charges. And what is an electric charge? Well, electric charge is just a physical property of matter. We represent it by a capital letter Q or lowercase q. At this point, you should be perfectly used to the fact that lots of quantities in physics have symbols that don't match the quantity's name at all. Now, any particle that has an electric charge will feel a force from any other particle that has an electric charge. It could be either an attractive force or a repulsive force. We'll get into that in just a moment. There are two flavors of electric charge, positive and negative. Now, electric charge is measured with a unit called a coulomb, and that's abbreviated with a capital C. But see, the thing is that a coulomb is actually a pretty huge amount of electric charge. So often it is more convenient to speak of electric charge in terms of millicoulombs, microcoulombs, or even nanocoulombs for very, very small amounts of charge. The elementary charge, often indicated by the lowercase letter e or q sub e, is the amount of charge carried by a proton or an electron. A proton and an electron both carry the same magnitude of charge, but with opposite signs, a proton being positive and an electron being negative. Now, as I said earlier, between any two charged particles there is a force known as the Coulomb force, sometimes also called the electrostatic force if the particles happen to be stationary. If the two charges have the same sign, that is, they're both positive or they're both negative, then they will repel each other, that is, they will push away from each other. But if the particles have the opposite sign, one being positive and the other being negative, then the opposite thing will happen. They'll attract together. They'll pull towards each other. So Coulomb's law is an equation that quantifies the attractive and repulsive forces between charges. If this law looks pretty familiar, it's because it's very similar to Newton's law of universal gravitation, which we talked about way back in Unit 4. Okay, but so instead of calculating gravitational force, we're calculating electrical force, and instead of using the gravitational constant, big G, we're using an electric constant, which is little k sub e. And instead of using the masses of two objects, we're using their charges. But the distance between them is still going to be squared. So just like Newton's law of universal gravitation, Coulomb's law is still an inverse square law, which means that whenever you double the distance between two charges, the electric force between them gets reduced to 1/4 of its original value. Remember that charges can be positive or negative. If you multiply two positive charges together, then the value of the Coulomb force is going to be positive. Likewise, if you multiply two negative charges together, then the value of the Coulomb force is positive. So, when two charges have the same sign of force, then the force between them is positive, and that indicates that the objects are pushing apart from each other. A repulsive electric force has a positive sign. However, when you multiply a positive charge by a negative charge, you're going to wind up with a negative value for the Coulomb force, which indicates that these two particles or these two charges are attracting towards each other. So let's take a look at our first skill practice question for this new unit. The problem says, calculate the Coulomb force between a positive 1.0 microcoulomb charge and a negative 3.0 microcoulomb charge if they are 0.50 meters apart. So we are going to use Coulomb's law to solve this problem. F sub E is equal to K sub E multiplied by Q1 times Q2 all over R squared. So this is really just a situation where we have to plug in these numbers and then chug out an answer. So KE is equal to 8.99 times 10 to the 9th newtons times meters squared per coulomb squared. And I don't think I pointed this out to you on the previous slide, but this is the value for Ke, and you will use this value for any problem using Coulomb's law. And the unit, newtons times meter squared per coulomb squared, it has to be that way so that when you plug in all the other numbers and do the math, it works out to be just newtons. It will leave just newtons for your final answer. All right, now let's plug in the value of the two charges. So the first charge is positive 1.0, and it says microcoulombs. So micro is times 10 to the minus 6 coulombs. So we want to put it in just regular coulombs, not microcoulombs. And then the second charge is negative 3.0 times 10 to the minus 6 because it's also microcoulombs. And then the distance between them is 0.50 meters. And you do not want to forget to square that. Okay. Square it, then you would not come up with the correct answer. So I'm not going to walk you through all the steps of this. You can punch it into your calculator. Please do be careful when you're entering numbers in your calculator in scientific notation. I strongly recommend that you use the format 8.99E9. Okay, do not try to type in times 10 raised to the 9th power. You'll just wind up confusing your calculator and probably getting the wrong answer. So use that E signifier if your calculator has that ability. If you have a scientific calculator, it probably does. So we'll multiply all these numbers together and divide by the radius squared, and you should come up with a number of negative 0.108, and it's going to be newtons because meters squared is going to cancel out with meters squared. We've got coulombs times coulombs, so that's coulomb squared, and that's going to cancel out. And so the only thing that does not cancel out is newtons, and that will be the unit of our final answer. And the answer should be negative because remember we had a positive and a negative charge, so they're going to attract towards each other with a force of negative 0.108 newtons when they are half a meter apart. Let's take a look at our next problem. It says two identical charges of positive 2.00 microcoulombs are being separated. At what distance will the force between them be 100 newtons? So we're going to use Coulomb's law just like in the previous problem, except this time we will be solving for R instead of solving for E. So we have Fe is equal to Ke multiplied by Q1 times Q2 all over R squared. And we do know the value of Fe. The value of Fe is positive 100 newtons. And the value of K, as always, because it's a constant, is 8.99 times 10 to the 9th newtons times meters squared per coulomb squared. And let's go ahead and plug in the value of the charges. Now, both charges are positive 2 microcoulombs. So I'm going to save a little bit of time. Instead of writing out positive 2 microcoulombs times positive 2 microcoulombs, I'm just going to write positive 2.00 times 10 to the minus 6, because it's micro coulombs, and I'm just going to square that number. Now I can only get away with this because both charges have the same magnitude. If the charges had different sizes, then I would need to write them out, obviously side by side. I can't skip if they're different charges. Alright, so we have everything set up that we need. I'm going to start by dividing both sides by Ke, and it will tell you that on the left hand side we now have 1.11 times 10 to the negative 8th. And the units, since we just divided out the newtons, and this was in the denominator, so this fraction is going to get inverted. So we're going to have coulomb squared, meter squared, which is a weird unit, and it doesn't really mean anything. It's just an intermediate step towards solving our problem. On the right-hand side, we have positive 2 microcoulombs squared. So that is going to give us positive 4.00 times 10 to the minus 12th coulombs squared. And again, what is a coulomb squared? It doesn't really matter. It's all going to come out in the wash in just a few minutes. And then on the bottom, we still have R squared. So we have R squared is equal to positive 4.00 times 10 to the minus 12 coulomb squared. all over, just a little bit, all over positive 1.11 times 10 to the minus 8th coulomb squared meter squared. All right, so when we do this division, coulomb squared is going to get canceled out. We punch this into our trusty calculators and we get 3.40, excuse me, that is not correct. My fault. We get 3.60. I wrote it down ahead of time so I wouldn't have to waste your time punching the numbers into the calculator, but it doesn't do much good if I don't copy. 3.60 times 10 to the minus 4 meters squared. And then we're almost there. We have one more step. We're going to take the square root of both sides. The square root of 3.60 times 10 to the minus 4 is going to give us 0.0190 when we round it to 3 significant figures. And that's going to be meters. So the charges will experience a repulsive force of 100 newtons when they are 0.0190 meters or 19 centimeters if you apart from each other.
Hey guys, we're going to go ahead and stop lesson 8.1 there. We're about halfway through, but the video got a little bit longer than I was expecting it to, so we'll come back tomorrow and finish up the end of lesson 8.1. In the meantime, I will go ahead and put a very short Google Doc on Google Classroom if you could take care of that. I appreciate it very much. And as always, I hope you're taking care of yourselves. Keep washing your hands. Talk to you tomorrow. Bye.